We are opening the meeting with the Earl Raymond Hedrick Lectures, named in honor of the first president of the Mathematical Association of America. Our speaker this morning is Professor John Milnor of Princeton. Professor Milnor received his PhD degree at Princeton in 1954 and was made a full professor in 1960. He is now chairman of the department. Among the honors which Professor Milnor received was one of the two Fields Medals awarded at the International Congress of Mathematicians in 1962. This was given for the best mathematical work of the preceding 4 years. He was elected to the National Academy of Sciences in 1963. In regard to his work, while an undergraduate at Princeton, he gave a solution of an important unsolved problem in topology. The folklore is that this was under the impression that it was a class exercise. I believe this was the case. He's noted for his work on the differential structure of a seventh sphere. Before this work, it was believed that the differential structure of a sphere was determined by the homotopy groups of the sphere. Milnor showed this was false, giving three essentially different ways of imposing a differential structure. I take great pleasure in introducing Professor Milnor, who will speak on the topic differential topology.
In order to start talking about differential topology, I have to first give a few definitions. The basic definition that I'll use will be the following. We'll consider always subsets of Euclidean spaces. So I'll start out with a Euclidean space of dimension k, and a point x in Rk, by definition, is a k-tuple of real numbers. And next we have to define the concept of a smooth mapping between Euclidean spaces. Or more generally, I'll consider an open set, say U in Rk, and a mapping F from this open set to some other Euclidean space Rl. And we'll say that such a mapping is smooth F is smooth if all partial derivatives are defined and continuous. So if all, say, nth partial derivative of f with respect to xi1 up to xin, if all possible partial derivatives are defined and continuous. This is the basic definition, and all of the rest of the subject will depend on this definition. So perhaps I should make a couple of remarks as to why one picks this particular definition of the concept of smoothness. Why does one require all possible derivatives? Wouldn't it be, in most parts of mathematics, one needs derivatives? It's usually enough to assume that you have one derivative or perhaps three derivatives at most. The answer is that it's really a matter of laziness, that we want to pick the definition which will make the subject easiest to handle, and this turns out to be it. If we only required three derivatives, then we'd have the difficulty that every time we took a function and took its derivative, we would only have two derivatives left. We would have changed the class of mappings we're working with. Using infinitely differentiable functions, we can keep differentiating over and over without ever losing anything. Or you might think that we should work with real analytic functions, functions which have a power series expansion. Well, that could also be done, but the difficulty there is that it's a little harder to construct real analytic functions. The fact is that it's very easy to construct infinitely differentiable functions making use of a certain standard building block, which comes up over and over again. This is a function which is a counterexample to the principle of analytic continuation. The function which is of let me call it lambda of t, which is 0 for t less than or equal to 0, and is equal to e to the minus 1 over x, e to the minus 1 over t for t greater than 0. So the graph of this function lambda is 0, and then it goes up like this. And this function does have the property that it's infinitely differentiable, and yet it's 0 for a considerable segment. And the existence of such a function is extremely useful and comes up over and over again in all of the theory. Well, I'm sorry, I have to go back now and start describing what differential topology is about, and I need to make more definitions. I've defined what it means for a mapping defined on an open set to be smooth, but suppose we have a more general situation. Let's have two Euclidean spaces, say Rk and Rl, and suppose we have a set X here and a set Y in Rl, and a function f from x to y. I'll write it this way. F is a function from x to y. What does it mean for f to be smooth? Well, by definition, f is smooth if locally it can be extended to a smooth mapping. So f is smooth if the following is true. Given a point f, x in x, if given x in x, we can find a neighborhood of x, say a little ball around x in the Euclidean space, and a smooth mapping from this neighborhood to RL, which is compatible where both are defined. So, say there exists a neighborhood U of x in Rk, and a smooth map capital F from U to RL, which coincides with little f whenever both are defined, namely on this common set of definition. I'll write it this way, with f restricted to the common range of definition, namely x intersect u, equal to capital F restricted to the common domain of definition. The end of the definition. So this defines a concept of smoothness between mappings. The concept of smoothness of a mapping between subsets of Euclidean space. And now we notice a few basic properties. The most important property is that the composition of any two smooth mappings is smooth. That is, if we have this situation, suppose x is in one Euclidean space, y in another Euclidean space, and z in another Euclidean space. We have mappings f and g. Then if f and g are smooth, then so is the composition. G composed with f, which is now mapping from x to z. And then we can make whenever we have such a situation where we have a concept of particular kind of mapping defined, such that the composition of mappings is again of this particular kind, we have a corresponding kind of isomorphism. And in differential topology, the concept of isomorphism is given a special name, namely diffeomorphism. So we can give a definition. F, mapping x to y, is a diffeomorphism if it's smooth and if it has a two-sided inverse which is smooth. So first condition is that F is smooth. And the second is that F has a two-sided inverse say G, mapping Y back to X, which is also smooth. In other words, saying it's a two-sided inverse means that if we apply first F and then G, the composition is the identity map of X. And similarly, if we apply first G and then F, composition is the identity map of Y. And if that happens, if we have such mappings in both directions, then we say that X is diffeomorphic to Y. And so now we're beginning to be ready to make a definition. As a first approximation, we can say that differential topology studies properties of sets which are invariant under this concept of diffeomorphism. This is fine, but there's one difficulty. I haven't put any restriction at all on our sets yet, except that they're sitting in Euclidean spaces. So they can be very, very wild indeed. We can have any kind of sets occurring. And I'd like to restrict attention to sets which look reasonably respectable. And so we make another fundamental definition. So far we've restricted mappings to being nice and smooth. Now I want to restrict our attention to sets in Euclidean space which are also smooth. In particular, the kind of sets we would like to use are ones which have a tangent plane at each point. This tangent plane should vary continuously as you vary the point, and in fact it should vary smoothly. So we want to look at sets in Euclidean space which at each point have a tangent, and this tangent should be a smooth function of the point. And the good definition turns out to be the following. Again, I consider a set X in Rk. I want to know what it means for X to be a smooth manifold of dimension F, say M. So the definition is the following. X is a smooth manifold of dimension M, or sometimes one says simply that it's a smooth M manifold, if locally it looks like the Euclidean space Rm. And looks like is to be interpreted in the sense of our category, smooth mappings. So the definition is the following. If each point of X has a neighborhood I'll use the following notation. I'll use the notation U for an open subset of the whole Euclidean space. Now, what I want is actually a relative neighborhood, a neighborhood in the subset X. And to indicate that, I'll write X intersect U, where X is the given smooth manifold and U is an open set in the whole Euclidean space. Each point of X has a neighborhood X intersect U, which is diffeomorphic to an open subset of Rm. Now this is the basic definition, so perhaps we should stare at it a while. let me again draw a picture. Suppose we have, let me take an example of a two-dimensional manifold in three-dimensional space. So this is a surface X in 3 space. And we want to compare this with the Euclidean space R2. Now, in saying this is a smooth manifold, we're saying that given any point here, we can find a relative neighborhood and a diffeomorphism between this neighborhood and some open set in R2. Let's call this diffeomorphism, say, going in this direction, H. And we can indicate this schematically as follows. Suppose that we take the coordinate lines in the plane. These will correspond to a certain grid of curved lines on our open set on the surface. And this will be a diffeomorphism. That means that H, first of all, that H is smooth. As all partial derivatives of the various components of H with respect to the coordinates in Euclidean space are defined and continuous. And H inverse is smooth. Given any point here, we can extend H inverse to a map defined in a little open set with all partial derivatives defined and smooth. And there's various vocabulary which is developed over the years. Such a mapping from an open subset in Euclidean space diffeomorphically onto part of a manifold is called a parametrization. Of the open set H of, let me call this U, H of U. As we're setting up parameters on a certain portion of our manifold. Let's say, giving them coordinates in some other Euclidean space. Or one also looks at the inverse mapping. H inverse mapping H of U back to U. This is also a smooth mapping by our definitions, and this is called a coordinate system. Notice that if we're given such a coordinate system, we can look at the various coordinate functions on the Euclidean space Rm, R2 in this case. So if we look at in this case, there are 2 different coordinate functions, the x-coordinate and the y-coordinate. Each of these gives us a certain smooth function on this open set. And these two smooth functions are called local coordinates on the open set H of U. Well, this then defines the subject matter of differential topology. The objects we want to look at are smooth manifolds in Euclid. I'm looking only at smooth manifolds in Euclidean space. One could make a more general definition, but I think this will be enough for what I want to do. And an important thing to realize is that we have what's called a category. That is, we have a certain collection of objects, namely the smooth manifolds in Euclidean spaces. And we have a certain collection of mappings, namely the smooth maps between smooth manifolds. And these have 2 basic properties which make this into a category, namely if F and G are smooth, then and if the composition is defined, then the composition is smooth. And the second property is that the identity map of any smooth manifold is smooth. Identity maps are always smooth. And more generally, any collection of objects and mappings satisfying these 2 conditions is called a category. And in any category, there's a corresponding notion of isomorphism. Here, the concept of diffeomorphism. And now we can state one of the central problems of differential topology. How can we suppose we're given two objects, two smooth manifolds. How can we decide whether they're diffeomorphic or not? This is essentially a problem that goes back to the beginnings of topology. There are familiar examples. For example, one ancient result is that one Euclidean space is diffeomorphic to another if and only if they have the same dimension. Another result is that one can classify surfaces. For example, one can distinguish between a spherical surface, which is one smooth manifold, or a surface of a torus. These are both examples of smooth manifolds of dimension 2, or there are surfaces of higher genus. This is the surface of genus 3, for example. These are all smooth manifolds in Euclidean 3 space, and it's a theorem that if you make a list consisting of a surface of genus 0, genus 1, genus 2, genus 3, and so on, this will give us precisely all smooth manifolds in 3 space which are compact, have no boundary. Of course, if there are other smooth manifolds which aren't in this list, things like the Möbius band. This is also a smooth manifold in 3 space, but it's not compact. It has in order to make it a manifold, in the sense of my definition, I have to take off this boundary curve, and that means we have something which is non-compact. Or there are other two-dimensional manifolds, such as a Klein bottle, but that can't be embedded in Euclidean 3 space. It can be embedded in Euclidean 4 space. So if we go into 4 space, we'd have more surfaces to add to our list. But I don't want to go into that. I'm just giving examples of smooth manifolds. So that's one problem then, to try to give some classification of manifolds or decision as to when two manifolds are diffeomorphic to each other. Or a closely related problem is to try to characterize the simplest manifolds. For example, the sphere of dimension n is a basic example. Sphere Sn is by definition a subset of the Euclidean space Rn plus 1, X in Rn plus 1, such that the sum of the squares of the coordinates is equal to 1. So, for example, I can draw pictures of the spheres of dimensions 0, 1, and 2. We take the Euclidean space R1 and look at all of the origin here and look at all points whose square is equal to 1. We get 2 points, plus 1 and minus 1. So a zero sphere consists of just 2 points. In the plane, R2, we get the unit circle as a set of points whose xy, such as x squared plus y squared equals 1. And finally, in 3 space, we get the unit sphere S2. So these are basic examples of smooth manifolds, have a similar definition in all dimensions. And the basic problem would be, how can we decide whether or not a given manifold is diffeomorphic to a sphere? So far now I've been trying to describe what differential topology is. Let me try to take a different point of view now and talk about what it isn't, namely by talking about other kinds of topology. I like to try to classify topology into 4 different parts. 4 different kinds of, if we like, there are 4 different categories that one can work with. And First of all, we've been talking about differential topology. Here the basic objects are smooth manifolds. So manifolds with a smoothly turning tangent plane. And the basic mappings are mappings which are also smooth. So in terms of, say, the mapping from the real line to itself, mapping is smooth but has a graph with a smoothly turning tangent which is never vertical. There's a second branch of topology which in many ways is similar to differential topology. That is the field of piecewise linear topology. And here the basic objects which one studies are simplicial complexes, objects made out of angular pieces. And the basic mappings one studies are piecewise linear mappings, that is, mappings which are made up of, whose graph is made up of angular pieces. Suppose this is again I consider a function from the real line to the real line. We'll have a graph, and if the graph is made up of straight line segments like this, then the mapping is called piecewise linear. Now clearly these two subjects are quite different. It almost never will happen that a simplicial complex is also a differentiable manifold. Essentially the only examples are planes, or open sets in planes. So that's the overlap between these two subjects seems to be almost nil. And yet it turns out that many of the techniques which are used in studying one can be adopted to work in the other. Then there's a third subject which seems to enclose both of these, and I don't really know what name to call it. I'm simply be forced to call it topological topology. Here we look at, so far I've been working only with subsets of Euclidean space, and let me continue to do that. Here the objects we look at are arbitrary subsets of Euclidean space. And the mappings we look at are arbitrary continuous functions, maps. So in terms of the picture, we look at a completely arbitrary set, and the mappings are not completely arbitrary, but they are required to be continuous, so that something like that is allowed. So here, so far I've listed three different kinds of topology, and each one is characterized by a certain category. We have objects which we look at in each of the three cases, and an appropriate concept of mapping. And in each case, this fundamental question would be the isomorphism question. Given two objects in the category, how can we decide whether or not they're isomorphic? In this case, we talk about diffeomorphism. In this case, in the third case, about homeomorphism. Two sets are homeomorphic if there is a mapping between them which is continuous and has a two-sided inverse which is also continuous. And in this case, we talk about piecewise linear homeomorphism. There's a homeomorphism which is piecewise linear, and it turns out then automatically that the inverse will be piecewise linear. Now these three subjects all go back to the beginnings of topology. That is, these three kinds of object, the arbitrary sets, the simplicial complexes, or the smooth manifolds, have all been looked at since the beginnings of topology, and that is perhaps 50 or 60 years ago were first considered. And so in a sense these are all old subjects. But the realization that that one really does have three different subjects here is quite recent. Up till in the beginning, one assumed that these were just different variations on the same subject, and that it was just a matter of technique and convenience which concepts one wanted to use. That is, well, sometimes one looked at smooth manifolds, sometimes at simplicial complexes. One could look at the concept of homeomorphism or piecewise linear homeomorphism. One assumed that these were essentially the same concept and that it was just a matter of hard work and a little luck to prove that these different isomorphism notions were the same. But it's turned out in the last 2 years that this really isn't true, that we really do have 3 different subjects and that each one has to be studied on its own merits. Now, I mentioned 4 different kinds of topology. So far I've listed 3. The 4th is a little different. It's the field known as homotopy theory. And this is a subject which was invented in the 30s when it was discovered that the first 3 kinds of topology were too difficult. One found that you simply couldn't solve most of the problems you wanted to ask, and so I think perhaps Hurevich was the first to invent an easier kind of equivalence isomorphism notion which made it possible to really attack problems. The basic definition here is the following. Let me start with this topological category of sets and continuous mappings. And if we have 2 mappings F and G from X to Y, we define F to be homotopic to G if there is a continuous deformation of F into G. And in more formal language, that comes out as the following. If there is a continuous map capital F going from X across the unit interval. So when I say you can deform small f into small g, I mean that there's a motion depending on a parameter, which we can think of as varying from 0 to 1, such that for t equals 0 we have the map small f, and for t equals 1 we have the map capital F. In more formal language, that comes out as the following. There exists a continuous map with f of x0 equals small f of x for all x and capital X, and f of x1 equals g of x. So we've now defined an equivalence relation between mappings, the relation of homotopy. And now we can talk about a new category in which we have the same objects as before, but we consider homotopy classes of mappings in place of actual mappings. Now, I've made this definition based on category number 3, the topological category, but we could do the same thing in the piecewise linear category or the differentiable category. Again, we can define the notion of differentiable homotopy or piecewise linear homotopy. And here it really turns out that it doesn't matter. We'll get very much for example, if we have two smooth mappings, it turns out that they're smoothly homotopic if and only if they're topologically homotopic, continuously homotopic. So the distinctions between these 3 categories blurs very much when we pass to the 4th, and we consider 1/4 category, the category of spaces and homotopy classes of mappings. And there's an appropriate notion of isomorphism here. Suppose we have x and y and a mapping f from x to y. When should we consider this to be an isomorphism in this 4th category, homotopy theory? Well, again, to be an isomorphism, it must have a 2-sided inverse. So now the name given to the concept of isomorphism here is homotopy equivalence. So F is a homotopy equivalence if there exists a mapping G from Y back to X. And I want to say that G is a 2-sided inverse, but now in the sense of my new category. So what does it mean to be a 2-sided inverse? So that the composition, first F and then G. Now I want to say not that this is the identity, as we said before, but only that it belongs to the same homotopy class as the identity. So that this mapping and F composed with G, mapping Y into itself, are homotopic to the respective identity maps. So this is the basic notion, and if that happens, then we say that x and y belong to the same homotopy type. And now I explained that one of the basic motives for introducing this subject is that it's easier than topology in many cases. It's a much easier question to decide whether two spaces have the same homotopy type than to decide whether they're actually homeomorphic or piecewise linearly homeomorphic or diffeomorphic. Let me give just some easy examples. For example, we might say in the case of differential topology, we looked at Euclidean spaces, and it's almost trivial to say that two Euclidean spaces are diffeomorphic if and only if they have the same dimension. But in terms of topology, the same thing is true. Two Euclidean spaces are homeomorphic if and only if they have the same dimension. But this is no longer trivial. It took a good deal of hard work about 50 years ago to prove this theorem. But in the fourth category, the category of homotopy theory, the whole problem disappears. Because if we take a Euclidean space Rk and a point, which I'll call R0, these have the same homotopy type. And proof, well, we have to give a mapping from Rk to R0, and there's no great thought required here because there is only one mapping from Rk to R0. And we have to take a mapping from R0 to Rk. Well, let's just take the embedding of R0 into the origin of Rk. And now I have to look at the two compositions. If we go from R0 to Rk and back to R0, well, again, there is only one mapping from R0 to R0, so we have to get the identity. And the other way, from Rk to R0 to Rk, so we get the mapping from Rk to itself, which I'll call 0. It sends every point to the origin. So in order to prove that these mappings are homotopy equivalences, I just have to prove that this 0 mapping from Rk to itself is homotopic to the identity. And proof, I'll define f mapping Rk across the unit interval into Rk by the formula f of xt equals t times x. Here I'm thinking of x as a vector and t as a real number between 0 and 1. This is the usual multiplication of a vector by a number. And then we see that f of x0 is always equal to 0, and f of x1 is always equal to x, so that we have a homotopy between the 0 mapping and the identity mapping. On the other hand, the homotopy theory doesn't kill all of topology. There are many other spaces which do not have the same homotopy type as a point. An example would be a sphere. It's a well-known theorem that no sphere has the homotopy type of a point. Well, let me try to compare these four categories, four different kinds of topology. And in order to compare them, I'll take one fundamental central problem in topology and see what the answer to this problem looks like in each of the four categories. And the problem I'll take will be the one I mentioned before, the problem of characterizing the unit sphere. Well, I have to be a little careful here. I said that I wanted to look at the same problem in each of the four categories. Now, what is the problem? In the first category, the category of differentiable topology, we have the unit sphere Sm contained in Rm plus 1 defined as before. It's a smooth manifold. All points with distance 1 from the origin, in Euclidean distance. The second case, the category of simplicial complexes and piecewise linear mappings, I can't consider this same sphere. It's not a simplicial complex as it stands. It's rounded, and this is a category in which I can only look at angular objects. So for this purpose, we have to think of some angular object which, in some sense, will be similar to the sphere. Well, the easiest object to take is the boundary of a cube. So it's, let me write it this way, boundary of Im plus 1, and in Rm plus 1. Im plus 1, I mean simply the, let me take as I, the interval from -1 to 1. Im plus 1 is the set of all m plus 1 tuples, each of whose coordinates lies between -1 and 1. And the boundary is the set of all m tuples such that at least one coordinate is equal to either 0 or 1. So, some figure such as this. And now why do I say that these two are essentially the same? The reason is that in terms of the third category, they are the same. In terms of the third category, there's a homeomorphism mapping this onto this. It can be defined very simply. We take the, notice that each of these has been defined so that the origin sits in the center. So we think of the unit sphere. I guess it will actually lie inside the unit cube the way I've defined them. It's inscribed in the unit cube. Well, pardon me, this picture isn't very good, but in each case we have the origin at the center, and we have a natural homeomorphism between the sphere and the cube as follows. Given each point on the sphere or the cube, we draw a ray going out from the origin. Each such ray intersects the cube in just one point and intersects the sphere in just one point. And this correspondence between points which lie in the same ray through the origin defines our homeomorphism. So in terms of the third category, it doesn't matter which of these two objects we look at. And a fortiori, in terms of the fourth category, the category of homotopy theory, it doesn't matter which of these objects we look at. So in each case, we have a standard object, which I'll simply call a sphere. And the problem is how to characterize it in terms of the isomorphism within the given category. And now, I said that the fourth category was introduced because it was easier to work with than the others. So let me first look at the answer in terms of category 4. So the problem is, which topological spaces have the homotopy type of, say, the sphere Sn. And to simplify things, let me assume that n is at least 2. Well, this problem has a very easy, or a problem which is considered very easy by homotopy theorists. There are three things one has to check. First thing one has to check, let me give name x to an arbitrary space. So we have a topological space x. We want to know whether it's homotopy equivalent to the sphere Sn, whether it can be distinguished by homotopy type invariance from the sphere. The first condition is that x is simply connected. That's why I put on the condition that the dimension should be at least 2. The sphere S1 is not simply connected, so I would have to alter the description somewhat. What does it mean to be simply connected? That means that every mapping from the sphere S1 into X is homotopic to a constant mapping. Or an alternative definition in terms of the concept of covering space, X doesn't have any covering spaces which are non-trivial. For the second condition, I have to use the concept of homology groups. These are basic tools of homotopy theory, or basic tools of all of topology, and I don't have time to go into the definitions. I can just describe basically what the properties of homology groups are. The homology groups give a correspondence from category of topological, from the category number 4, say topological spaces and homotopy classes of mappings, to the category of groups and homomorphisms. So that means that, well, let's see, I was going to write down condition 2 here. Condition 2 is that X has the homology of the sphere. Sn it was. Now, to explain this, I'd better go to the other view graph. What are homology groups? Well, I'll simply describe their properties. First, properties of homology groups. Properties. First property is that to each space X, each integer I greater than or equal to 0, there corresponds an additive group called HI of X. And the second property is that to each mapping F, mapping X into Y, there corresponds F star mapping HI of X to HI of Y. This is a continuous mapping between spaces, and one gets a homomorphism between additive groups. And there are many other properties which I can't go into, but I can simply describe what the homology of a sphere Sn is. So if I take X equal to Sn, and here I'd better assume that n is at least 1, then we have the following description. HI of X, homology group, is infinite cyclic for I equals 0 in n, and it's 0 otherwise. So in other words, we say that a sphere has homology in dimension 0. It is an infinite cyclic group in dimension 0 means simply that it's connected. It has homology in dimension n. Infinite cyclic group in dimension n describes in some sense that there's an n-dimensional cycle covering the sphere. It has no homology otherwise. And so this is the condition we want to assume, that HI of X, where here I mean more standard terminology, the ith homology group of X with integer coefficients is infinite cyclic for I equals 0 in n and 0 otherwise. Well, what I have now, conditions 1 and 2, essentially give a characterization of the sphere in terms of homotopy theory. I have to stick on one extra condition, however, which says that X is not too pathological. Third condition is that X has the homotopy type of some say, simplicial complex. This is just a condition to rule out pathological examples. Given this condition, then we just need a condition that X have the right homology and the right fundamental group, that it be simply connected. And then it's a standard theorem of homotopy theory that given these conditions, X must actually have the homotopy type of the n-sphere. So these various tools, the fundamental group and the homology groups, are the basic tools of homotopy theory, so that it's extremely satisfactory that one has an answer in terms of these basic tools. The third condition is one that one always has to assume to get anywhere in homotopy theory. One doesn't want to look at pathological objects, so that one really has a complete and satisfactory answer to this characterization problem in the area of homotopy theory. Now, what happens if we go to one of the other categories? Well, I seem to be getting close to the end of the time, so let me just describe the answer very briefly. Have the category of smooth manifolds, the category of piecewise linear piecewise linear objects, or in other words, simplicial complexes, and finally the category of topological spaces. Well, the answer in the third case is that no one knows. Well, that's perhaps putting it a little too strongly. The problem was to characterize the sphere as a topological manifold. There exist characterizations. Certainly, classically, there have been characterizations of the one sphere and the two sphere. And if one makes extra assumptions, such as the assumption that the space is homeomorphic to some smooth manifold, for example, then there are characterizations in higher dimensions. But what I mean when I say that nothing is known is that if we just have the condition, just a topological space, and no condition of the sort that it can carry a differentiable structure or that it's homeomorphic to some simplicial complex, then I don't think there are any really satisfactory conditions. But I think perhaps I'd better cross that out and come back to the subject later. That's really an extreme oversimplification. In the category of simplicial complexes, one has a very satisfactory answer, providing that the dimension is at least 5. There is a theorem that if we have a simplicial complex of dimension at least 5, it satisfies certain very simple conditions, then it will be piecewise linearly homeomorphic to a sphere. This essentially is due to Smale. In the case of smooth manifolds, the answer is that what we've defined is an interesting problem. It doesn't have an easy answer, but one has to give many conditions. There are no easy conditions, but it is a problem which one can effectively handle. So again, I can't in 1 minute describe what the answer is, but I'll hope in the next hour to try to describe what one can say about the problem of characterizing the sphere as a differentiable manifold.